Hello everyone, my name is Supriya, working as Assistant Professor in the Department of PG Studies and Research in Statistics, SDM College Autonomous Ujre. I am going to speak on the topic that is coefficient of determination, and then I will be introducing the concept of multiple linear regression. Coefficient of determination, we denote it as R square, which is equal to regression sum of square divided by total sum of square. Since we know that total sum of square is equal to regression sum of square plus residual sum of square, so thereby we can define coefficient of determination R square as 1 minus residual sum of square divided by total sum of square. Since total sum of square is a measure of the variability in y without considering the effect of the regressor variable x, and the residual sum of square is a measure of the variability in y remaining after x has been considered, thereby we can interpret the coefficient of determination R square as the proportion of variation in y being explained by the regressor x. Since the value taken by residual sum of square lies in between 0 and total sum of square, so thereby the value taken by coefficient of determination lies in between 0 and 1. Values of R square closer to 1 imply that most of the variation in y is being explained by the regression model. Let us consider an example. Suppose we get R square as 0.9018. So this means that 90.18% of the variability in the response is accounted for by the regression model. Now let us consider some note regarding the coefficient of determination R square. The statistic R square should be used with caution because it is always possible to make R square large by adding enough regressor variables to the model. The magnitude of R square also depends on the range of variability in the regressor variable x. So generally R square increases as the spread of the x increases and decreases as the spread of the x decreases, provided that the assumed model form is correct. In general, R square does not measure the magnitude of the slope of the regression line. It does not measure the appropriateness of the linear model because R square can be large even though x and y are non-linearly related. So thereby we can conclude that although R square is large, this does not necessarily mean that the regression model will be an accurate predictor. Now let us move on to the topic, that is multiple linear regression. So multiple linear regression model is an extension of simple linear regression model. So multiple linear regression is a regression model that involves more than one regressor variable that has linear relationship with the response variable y. Let us consider a real life example. Suppose that the yield in pounds of conversion in a chemical process depends on temperature and the catalyst concentration. So here we can consider yield as the response variable, temperature and catalyst concentration as the regressor variables. So our multiple regression model that might describe this relationship is given as y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. So this is a regression model with two regressor variables x1 and x2, where x1 denotes temperature and x2 denotes catalyst concentration. So here you can observe that in the model we call it as multiple linear regression model. So the term linear means the multiple linear regression model is a linear function of the unknown parameters beta naught, beta 1 and beta 2. And also the regression model that we define describes a plane in three-dimensional space of y, x1 and x2. So we can observe that there are three parameters in the model, that is beta naught, beta 1 and beta 2. The parameter beta naught is called as the intercept parameter. So it is the mean of the response when the regressors x1 and x2 takes the value 0. Otherwise beta naught has no physical interpretation. The parameter beta 1 indicates the expected change in the response y per unit change in x1 when x2 is held constant. Similarly, the parameter beta 2 measures the expected change in y per unit change in x2 when x1 is held constant. In general, we can relate response y to some k number of regressors or predictor variables x1, x2, so on up to xk. So thereby defining the multiple linear regression model with k regressors as y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus so on up to plus beta k xk plus epsilon. So here the parameters beta j, where j taking the value from 0, 1 to k, are called as the regression coefficients, and this model describes a hyperplane in the k dimensional space of the regressor variables xj. The parameter beta j can be interpreted as the expected change in the response y per unit change in xj when all of the remaining regressor variables xi where I naught equal to j are held constant. So due to this, we call the parameters beta j as partial regression coefficients. Multiple linear regression models are often used as empirical models, or they can be also used as approximating functions. Now let us look at some examples. The models that are more complex can still be analyzed by using the approach of multiple linear regression technique. So let us consider a cubic polynomial model, that is y is equal to beta naught plus beta 1x plus beta 2x square plus beta 3x cube plus epsilon. So here if we denote x as x1, x square as x2 and x cube as x3, then we get a multiple linear regression model with 3 regressors x1, x2 and x3. Similarly, if we consider a model that include interaction effects, that is y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 1 2, the interaction effect x1 into x2 plus epsilon. So here in this model, suppose I substitute beta 1 2 as beta 3 and x1 into x2 as the regressor x3, then we get a multiple linear regression model with 3 regressors x1, x2 and x3. Similarly, let us look into one more example, that is second order model with interaction. That is y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 1 1 x1 square plus beta 2 2 x2 square plus beta 1 2 x1 x2 plus epsilon. Here if I denote beta 1 1 as beta 3, x1 square as x3, beta 2 2 as beta 4 and x2 square as x4 and beta 1 2 as beta 5, x1 into x2 as x5, then we get a multiple linear regression model with 5 regressors, that is x1, x2, x3, x4, x5. So in general, any regression model that is linear in the parameters beta j's is a linear regression model regardless of the shape of the surface that it generates. So here in multiple linear regression model, the values of the parameters, that is regression coefficients beta j's and the error variance sigma square are not known, and they has to be estimated using the sample data. And after estimation, we obtain the fitted multiple linear regression model that is typically used in predicting the future observation of the response variable y or for estimating the mean response at particular values of the regressor variables. Thank you.